I will share my screen now to the problems. I hope I can have it projected, so if not, then just let me know. These are things that you can answer right away, but there are problems towards the end which we need to solve. Okay, so I can see now that you can see the application. So hopefully you'll be able to see. Let me know if you cannot see the slides, if I'm going to have it projected. I'm going to give you questions which you will answer. Um, answer in the chat box, okay? Let's see if this will work. So this supposed to be is the problem set, but I'm discussing it and we're giving you a different one, a different problem set which you will accomplish by group. Can you see the slide? The next slide. Can you see the slide, class?
Ay, Dok, hindi gid, Dok. Ang makita naman ang whole job mo, Dok.
Oh, see. So you will see now the answer. That is the case. Anyway. Sige. I cannot transfer to a different laptop because the what you call this, the one that I'm writing on cannot be installed on my MacBook, so that is why I'm using this one, which is I'm having really problem on. Anyway, sige. So for the unit of the K for a first order reaction, if you're given the following choices, so the unit for the K for a first order reaction is per unit time, if it's first order. Now, this is based on the fact that the unit for K, as discussed, the general formula for the set of units for your K is 1 over time times concentration raised to 1 minus n. So if the order of the reaction is 1, then you don't have this particular part there. So your unit for the K is just per unit time. Go to the second. Okay, in which of the following does the reaction go farthest to completion? So the given choices are all equilibrium constants. And we have learned that the greater the value of the equilibrium constant, the more difficult it is for the reaction to be 100% completed or to have an XA equal to 1. Now, primarily based on the fact that if you have a K which is very big, one particular uh, one particular direction in your reversible reaction is dominating the other. So the greater the value of this rate constant, or rather this equilibrium constant, not the rate constant, the reaction will never go to completion, or either you will never attain XA, which is equal to 1.0 or 100%. Now, next question. If the temperature of a chemical reaction is increased by 10 degrees Celsius, the rate of the reaction is increased by a factor of about 2. So there is this primary principle that for every 10-degree rise in temperature, the rate of the reaction doubles. So that is why this is the factor in which your rate of reaction is going to increase. Okay, next. Now, the activation energy, capital letter E, of a reaction will be lowered by, so you can lower the activation energy of a particular reaction by adding a catalyst. You cannot lower the activation energy by increasing the temperature, nor can you lower it by removing the products of the reaction. So the answer here is if you add a catalyst, that will lower the activation energy of your system. Now, the mechanism of reaction can sometimes be deduced from, or we can make a trial placement of the mechanism of our reactions, or the series of reactions that will bring about our overall reaction through the use of the rate of reaction, or that is the rate law. So from the rate law, we can see what particular reactants would be present in the overall reaction. And as such, we would know what particular reactant should be present in our series of steps, or in the mechanism of reaction that we are going to write. So based on the choices that we have in here, it is the rate of reaction, or the rate law, that will help us find the mechanism of the reaction. Now the mechanism, okay, that's the question that we just answered. So the law governing the kinetics of reaction is the law of constant composition. So it's not chemical equilibrium, it is not mass action, it's not constant temperature, but rather constant composition. So it is the law governing the kinetics of reaction. Now, the equilibrium constant in a reversible chemical reaction at a given temperature does not depend on the initial concentration. Where does the equilibrium constant depend on for a reversible reaction? Where does it depend on based on what we have discussed so far? So the answer, it does not depend on the initial concentration. So it depends on the final concentration. There's some error there. The equilibrium constant depends on the what? Based on what we have discussed last meeting. The equilibrium constant depends on the arnica. Where does the equilibrium constant depend on? Arnica, are you there? No, does not depend on the temperature. The equilibrium constant, where does it depend on? Aliyah? No, not on the rate of reaction either. Aliyah, where does the equilibrium constant depend on? Gerio, are you there? Aliyah? Where does the equilibrium constant depend on? Aliyah? Final concentration? No. Chobern already gave that one. Where does it depend on? Colleen, where does the equilibrium constant depend on? Colleen, where does the equilibrium constant depend on? If it does not depend on the initial concentration, where does it depend on? The equilibrium constant, the K sub EQ for reversible reactions. Conversion. Conversion at what? Stoichiometric coefficients? Could be, but this is lacking, Giselle. Stoichiometric coefficient and what? So there could be several factors in which your equilibrium constant could depend on. So Giselle, it does depend on the stoichiometric coefficient. However, the stoichiometric coefficient alone does not determine it. It goes with the what? Colleen, I was calling Colleen a while ago. Colleen, are you there? Are you in the room? Where does the equilibrium constant depend on? Temperature, no. Temperature is a factor in which our rate constant is dependent on, but not the equilibrium constant. Where is it dependent on? Based on the formula that we have, forward and backward reaction is what of the forward and the backward reaction? The equilibrium constant. Okay. Let me see. Order of reaction, miss. Power of the stoichiometric coefficients. Maybe what you mean is that the stoichiometric coefficients now are used as power. Power of what? It seems like Colleen is not in the room. Why is she not answering? Colleen Awit. Where is Colleen? Okay, waiting to be admitted. Okay. Up, equilibrium, concentrations, miss. Hi, salamat. Correct. Joshua, very good. Your equilibrium constant is dependent on equilibrium concentrations. So if you recall our discussion last meeting, this only tells me that you don't really follow what we're discussing. Maybe you wait for it when it's time for the quiz or when it's time for the exam to study. These are very fundamental questions that I'm asking you. The equilibrium constant, since your Chem 1 is dependent on the equilibrium concentration of the products, let's say you have here A plus B giving you C and D. Let's say I have here a 2A. So this would be now the C sub CE, C sub DE, C sub A squared, and C sub B. That's where your equilibrium constant is dependent on. It's dependent on the equilibrium concentrations of the products, not only the products and the reactants. As to what Giselle gave as an answer a while ago, so the stoichiometric coefficients are actually the powers to which these concentrations are raised to. Another factor in which your equilibrium constant is dependent on is, this is very elementary, the rate constant of the forward reaction, same thing with the rate constant of the reverse reaction. These are the formulas that we are using in determining the equilibrium constant. There's also another formula which is dependent on the equilibrium conversion. I'm saying XAE, but it's not one that is common, and it has to be derived from the type of reversible reaction that is given. So the equilibrium concentrations, the equilibrium conversion, and the rate constants of the forward and the reverse reactions are the factors that affect your equilibrium constant for a reversible reaction. It does not depend on initial concentration. So please follow through our lesson. Maybe you have a lot to study, but please follow up when we have a review, because these are already review. What I'm giving you are the basics actually. When it is asked on you, it's not anymore going to come to you as basic as the one that I am asking now. Okay, so we have the next question here. Which of the following statements is the best explanation for the effect of increase in temperature on the rate of reaction? So this would have been better if this is projected and you can choose from the choices. But in the 4 choices that's provided in here, the best explanation is this one. The reason why temperature is a factor that affects the rate of reaction is because it increases the number of particles with the necessary activation energy. So the more particles attaining the necessary activation energy, or that minimum amount of energy that will render it ready to react with another, then the faster is your reaction. So that is why temperature is a factor that affects the rate of reaction. It's because once temperature is increased, a lot or a greater number of particles already possess this minimum energy, which is the activation energy. The other choices here are not acceptable. So we only have this one for the best explanation that is being asked. It says here it's the best explanation. Now, if the rate of reaction is independent of the concentration of the reactants, the reaction is said to be This is elementary as well. It's zero order. Does not depend on the concentration of reactant. So a zero order reaction, as discussed, has its rate depending on some other factors. So it could be, especially for the photochemical reactions, it has something to do with the intensity of the light in which your reactor is exposed to. So it could be dependent on other factors other than the concentration of your reacting species. Now we will continue. The specific rate of reaction is dependent on temperature. You know this already. It's not dependent on the time of reaction, nor it's dependent on the heat of the reaction, nor on the concentration. The specific rate of reaction, which is the K, is dependent on the temperature. The rate of reaction is not influenced by. So it's not influenced by molecularity of reaction because it's dependent on concentration, it's dependent on the nature of the reacting species, and it's dependent on temperature, primarily because your K is temperature dependent. Molecularity is not an influencing factor for the rate of the reaction because in the case of non-elementary reactions, the number of molecules of the species as written in your stoichiometric equation does not whatsoever at all times boils down to something that we could use in writing our rate law, which gives us a picture of the rate of the reaction. Okay, there's somebody there in the inbox. Sorry, miss. It's okay, Marcel. Now, next, we will have the next one. Slide 13. For the reaction 2A plus 3B forming 2E, the rate is equal to K C sub A C sub B squared. The reaction is said to be non-elementary. So there is no connection with the rate law and the stoichiometric equation. So that non-correlation is telling you that the given reaction, this one, is non-elementary. Chemical reaction rates in solution do not depend on. So this is very important. Reaction rates for solutions, liquid solutions that is not dependent on pressure. This is only a factor to be considered when we are talking about gaseous reaction. But for liquid reactions or for solutions, pressure is not a factor in which the reaction rate will depend on. For the others here, of course, the rate is dependent on temperature, concentration, and the presence of the catalyst. Pressure is an added determining factor if we're talking about gaseous systems. So let me go to this one. 15. The overall order of reaction for this elementary reaction is third order. All you have to do is add the coefficients of the reacting species. So that gives you the order of the reaction. Total overall order, that is. But with respect to A, it's first order. With respect to B, it's second order. Now, I have it here. This would have been interesting if this is projected. If the volume of the container for your reaction A plus 2B forming C is suddenly reduced to 1/2 to its original volume, with the molecules of A, B, and C maintained constant, the rate will blank by a factor blank. So the answer here is it will increase by 8. Now, since you know already the answer that it will increase by 8, anybody here who can explain why decreasing the volume of the original system to half of its value while keeping the number of moles of the species A and B constant will result to an increase by a factor of 8, or it will increase 8 times the rate of reaction. Can somebody explain why is that? May I ask? Okay, let me see. Eugene. Eugene. Pass.
Hello, miss.
Okay.
Wait lang, good miss ha.
It's okay. It's okay. Now, like you to think why your rate of reaction will increase by 8 if a system's volume is decreased by 50%. That same question goes to, let me check, Jabi May. Are you there, Jabi May?
Miss.
Okay.
Hello, Miss.
Yes.
Nang base, hindi kita on, Miss, ang sa question sa PowerPoint, Miss.
Hindi kita ano ng question. I'm not projecting it. Yes, Jobern, you're raising your hand.
Based on what I've reviewed, Miss, di ba, Miss, ng 2 raised to n, doon may nakuha akong formula 2 raised to n, pero ang n, Miss, is the order, Miss, of the reaction. So 2 cubed is 8. So meaning may increase by 8, Miss.
Okay, so what you remember, Jobern, has something to do with for a second order reaction, doubling it, or a first order reaction rather, doubling it will be having a formula of 2 raised to n. It will increase the rate by 2 raised to n. Now, in this particular question, we're talking about the system's volume. The system's volume decreased by 50%. For it resulting to an increase in the rate of 800 times the original, or 8 times the original rate. So how do you explain that? Greater collision rate at lower volume. Late puro kasulod ang answer ni Colleen ay. Sige, Colleen, maybe this is an answer to my previous question. So I'm now waiting for the answer here. Why is it an increase by 8% for a third order reaction? Anybody? Can I ask another one? Let's see. The concentration will double. The concentration will double. Okay. Do you have your mic on, Joshua?
Hello, miss.
Okay, you
Yes.
have your mic on. So I'd like you to explain what you wrote to me here on the direct message. The concentration means will double. So if
Hindi
the
ako sure, miss.
explain. So can you
Like,
explain?
di ba, miss, ang rate of reaction is K is equals to concentration of A times the concentration of B raised to squared. So if ang volume niya half, meaning ang concentration niya is times 2. So which means mahimo siya 2 bali 2A
Your
times B.
concentration for A will become twice of the original.
Yes, miss. Then
The
times ko
concentration
siya
of B will
B2
also
squared.
be
Yes, miss.
twice the original. Now this concentration of B is raised to 2, right? Because it's having a coefficient of 2, making
Yes. Yes, no.
reaction. So that is why you will have an increase by 8. Do you get the explanation of Joshua? I'll write it here. I will annotate. Very good, Joshua. Very good. So this is it. Your rate is equal to K C sub A C sub B squared. As it is written here, based on the stoichiometric equation. Now, you have the original concentrations of A and B, right? You have, let's say, for example, 1 mole, let's say 2 moles for A, 2 moles per liter of A, and let's say 2 moles per liter of B. Now, if you're going to divide the volume or your system's volume into half of the original. So meaning the concentration of A and B will be twice of what it was before you have divided the volume, because you're going to divide it by 1/2. We know that concentration is equal to the number of moles divided by the volume. If this volume here, this one is kept constant, so it's maintained constant as stated there. So nothing happens to this, and this volume here will be B over 2. So what happens to this concentration here? This 2 goes up. So your new concentration, let's say C prime, will be equal to twice of the initial concentration when the volume is not yet decreased by 1/2. Do you get it? So that's the reason why if you have already the volume of each of the species of A and B increased by 2, or rather doubling, so this one will double and this one will double. The thing is this one is squared, so this will be squared. So you have 2 times 4, that would be 8, resulting to an 8 times resulting to a rate of reaction which is 8 times greater than the original. Do you get it? So that's it. You have to go back to the basics of what's concentration, of how we express concentration in terms of moles and volume, because it's stated here. Its original volume by 1/2, while the moles of A, B, and C maintain constant. So meaning you don't touch the end, you only alter the volume of your system. So I hope it's clear to everybody. So that's the reason why your rate of reaction will increase by 8. Okay, let's move on. So we're now on here. We're on 16. Then we'll have 17. The rate of formation of B in terms of RA, where rate in terms of A is equal to negative. Actually, this negative class should be written here. So let me just annotate. It's difficult if it's like that. Now, actually, this negative should be placed in here. Well, I'll just take it out from there. So the rate law in terms of A is K C sub A C sub B squared. What then is the rate of formation of B in terms of A? The rate of formation of B in terms of A. The answer is this. Do you see something wrong with the answer? So your rate in terms of A is equal to K C sub A C sub B squared. If this is the manner in which we write our rate law, on the assumption that we have an elementary reaction, your reaction would have been A plus 2B, right? Forming the products. So if you are very keen on the manner in which this particular problem is written, how will then be the rate of formation of B in terms of A? Rate of formation, isn't it B a species that is reacting? So if you're going to write down the relationship of rates, it would have been the rate in terms of A over 1 equated to the rate in terms of B over 2. It's negative because B is being consumed. It's not being formed. So the reason why it's positive here as written, it's because the rate of B is equal to twice the rate of reaction of A. But since it says here formation, B is not being formed, but rather it's being consumed. So that is why you see here A positive 2RA. If you multiply both sides by -1, that way your B will be written as a product, not as a reactant. Then it will be rate of formation of B will be the negative of this. So that would be now twice of the rate of reaction of A. So you don't see a negative sign here anymore because it's asking for the formation of B. If it's asking for the rate of reaction of B, then it would be something like this. It should be written as this one. Okay? The others are not acceptable because we are always basing relationships on rates, whether we have an elementary or non-elementary reaction on the stoichiometric equation or on your reaction itself. Now we go to 18. The net rate of reaction of an intermediate, especially in your mechanism of reactions, is 0. If you recall, when we did proving for the relationship of the provided rate equation or for the implied rate equation to the given mechanism of reaction, we write down the net rate of reaction of intermediates and we equate it to 0. It's because there is no net rate of formation nor net rate of disappearance for these intermediates. It's a 0. So that's the reason why we equate it to 0. When we did our proving then, in terms of correlating rates of reaction to provided mechanism. So the others are not acceptable. It's the 0 thing here that is the answer. So we proceed with 19. For the reaction 4A plus B forming 2C plus 2D, which of the following statements is not correct? It's so easy to spot the error, actually. If I'm going to ask you what tells you that it's the error without having to really like understand each of the statement, what word gives it away that it's not correct? Based on the choices here, our answer is the rate of disappearance of C is 1/2 the rate of consumption of A. So that's the statement that is incorrect. What gives it away without having to understand? Let's say, for example, you don't understand disappearance, 1/4, 1/2, 1, 1:1, or things like that. So the term disappearance, correct, correct. C is not disappearing, C is being formed. So that tells you that this statement is wrong already. Because in here, the rate of disappearance of B is disappearing. The rate of appearance of C here is being formed. So correct. The rate of formation of C also correct. But this one, the rate of disappearance of C does not disappear, but rather it's being formed. Okay, so that's it. Even if you don't need to look at the 1/4, the rate of disappearance of A, or 1/2, that the word disappearance gives it away. So that's the incorrect statement. Okay, we move on. The collision theory of chemical reaction maintains that the rate is directly proportional to the number of collisions per second. In a very old edition of Octave Levenspiel, there is this particular rate expression which I've shared also to you when we're taking kinetics, in which the rate is measured. This is in relation to a gaseous system. The rate is measured in terms of the number of collisions of similar species or dissimilar species of gases. If you can recall that, there's even a subscript AA and AB for that. So the collision theory maintains that the rate is directly proportional to the number of collisions per second of these particles in your system. So this is related to gaseous system. The collision theory is applicable to gaseous systems. Now we go to the next. A reaction is first order in A. A straight line will be obtained by plotting the log or the ln of Ca versus time. So this is what I mentioned to you, that there are questions that you think will not be coming out because the basis is on the graphical interpretation of the differential equation which you have integrated coming from the rate equation. But this question is actually taken from a reviewer, and it's like this. It's stated like that. So a reaction is first order in A. A straight line will be obtained by plotting the ln of Ca or the log of Ca versus time. Who can still recall our formula for first order reaction? What's the formula for a first order reaction? We have ln of Ca over CaO equal to Kt, right? Negative. So if you make it positive, you have ln of CaO over Ca equal to Kt. Then separate ln's. So ln of CaO minus ln of Ca is equal to Kt. ln of CaO, transfer this one in here. So I will have minus Kt. And this one in here, you have ln of Ca. So this is the y, this is the x, this is the m, and this is the b. So this is the correct answer here for the plot of your first order reaction. What's the relationship or what values you need to plot? So it's the ln or the log of Ca versus time. So it's a straight line. Okay, we go to the next. This one is similar to the previous one, it's talking of a different order. The activation energy, it's not yet the one that I have in mind. So the activation energy of a reaction can be obtained from the slope of the plot of log K versus 1 over T. If you recall again the equation, we have K equal to E raised to negative E over RT. This is our Arrhenius equation. So the activation energy of a reaction can be obtained from the slope of the plot of what? So you need to take ln of both sides. So you have ln E raised to E over RT. So ln of K is equal to negative E over R and 1 over T. This is the one that gives it away. This is the basis. The log or the ln of K versus 1 over T. Or if you can recall the relationships that became in terms of a pair of data. So E over R over 1 over T sub 2 minus 1 over T sub 1, something like that. So it's the reciprocal of the temperature and the ln of the K that we did in here. Okay, so but the line equation is this one. That's it. Now next. The reaction is 2A forming B plus C in second order. Which of the following plots will give a straight line? This one. If you recall, again, the formula for a second order reaction, this is case 2, bimolecular single species, case 2, because we have 3 cases under second order reaction. So this is case 2. You have 1 over Ca minus 1 over CaO equal to Kt. So you're going to have this as the y, this is the x, this is the m. You transfer this on the other side, that will be your b. So this is the plot of the second order equation. This is case 2. If you recall in your kinetics, there are 3 cases under second order irreversible reaction. It's the same thing with third order irreversible reaction. That's it. So your answer will be this. The others are not acceptable. Now, for the reaction A plus B forming 2C, when Ca is doubled, make this bigger. When Ca is doubled, the rate doubles. When Cb is doubled, the rate increases 4-folds. The rate law is this. If this doubles, the rate doubles, so meaning you don't touch this one. If B is doubled, the rate increases 4-folds, so meaning this is the one that I have mentioned a while ago, Joburn, with the 2 raised to n. So the n being the order of the reaction. So if there's a doubling in the concentration, there will be a 4-fold increase in the rate. So then the rate law is like this. Okay, we have this particular type of, I have presented this as well at the beginning of the review in terms of the data in tabular form. So if you're given a statement like this, it follows that when Ca is doubled, the rate doubles, B there is kept constant. When Cb is doubled, And when the rate is increased fourfold, A there is kept constant. So how would you write the rate law? So this is how you should write the rate law for this particular reaction that is given. Okay, so we go to 25. A pressure cooker reduces cooking time because, so we have the choices here. The boiling point is elevated, the heat is more evenly distributed, the higher the pressure or the higher pressure tenderizes the food, or a flame must be used. So the answer is this, of course. We increase the pressure, the temperature also increases. So that tenderizes the meat. So it reduces the cooking time because it tenderizes the meat faster. It elevates the boiling point. Okay, increasing pressure elevates the boiling point. Go to the next one. A catalyst can, so which of the following statement is best? So shift the equilibrium of the reaction, diminishes the activation energy, increases the rate constant of the forward reaction, decreases the pressure. So the purpose of the catalyst is to decrease the activation energy, decrease the needed amount of energy for your species to be rendered ready to react. That's the main purpose of the catalyst. Now, it states that the rate of the chemical reaction is proportional to the activity of the reactants. So that particular law is the law of mass action. The rate of the reaction is proportional to the activity of the reactants. That's law of mass action. By the way, why is it not Le Chatelier's? Who can remember Le Chatelier's? Who can remember second law of thermodynamics and Hess law? All of which are in thermodynamics, right? And you're done with your thermodynamics. You will be reviewed by Ms. Tashi on this. Why are these three not the answers? Who can recall Le Chatelier's? No one? Nobody can recall Le Chatelier's. What about second law, thermodynamics? Hala. Oh, thank you, may nagsulat. Entropy. Correct, Giselle. Something to do with entropy. What about entropy, Giselle? Where are you referring to? Le Chatelier's or second law?
Miss,
Come again?
it's in the second law of thermodynamics, miss.
Oh, what about entropy? Ano hambas ang second law of thermodynamics? I'm just curious if you can still recall.
The total entropy of a system could never decrease.
Could never decrease. So meaning everything eventually will really be approaching a degree of increased disorderliness. Muna ginahamba nila, balaki sa jokingly, especially if your working space or if your working table is already having piles and piles of paper and books in there and you don't really arrange them, say nila, that's entropy. That's second law of thermodynamics. There would only be there's a projection of a greater increase in disorderliness. So, hindi na siya magbalik sa dati. Amo na yung explanation ng science. So, it will just be a progressive increase in entropy. Okay, somebody wrote in the chat box. Le Chatelier's. Le Chatelier's, Giselle, what are you saying about Le Chatelier's? Le Chatelier's counteract the change means para ma-establish ni what ang equilibrium. Okay, so Joanna is saying that Le Chatelier's counteracts the changes so that ma-re-establish ang equilibrium. Okay, that's correct. But that's something that you will be discussing again in your thermodynamics. So Ms. Tashi will be discussing it to you. Or probably you're done already with your thermodynamics in your review 3. So this is already covered by Ms. Tashi. Okay, now we proceed because we still have a lot to solve in here at the latter part. The rapid increase in the rate of chemical reaction, even for small temperature increase, is due to, so you have 4 statements there to choose from. Rapid increase in the kinetic energy of molecules. Rapid increase in the temperature of the fraction of molecules with energies in excess of activation energy. Rapid increase in collision frequency, and increase in activation energy. All the statements seem to be correct, but the best one is letter A. So rapid increase in the rate of reaction, even for small temperature increase, is due to rapid increase in kinetic energy of molecules. Going back to every 10-degree rise in temperature will result to a doubling in the rate of reactions. When you choose class from provided statements, Bala, which of the following best explains this, that you always go back to the basic, to the fundamental, because you will never go wrong with that. Don't choose a statement that seems to be highfalutin that you yourself cannot understand. Go for the statement which you agree with and is simple, direct to the point. So in this case, this would be the answer. Rapid increase in the kinetic energy of the molecules. Now we move on. The half-life of a material undergoing second-order decay is inversely proportional to the initial concentration. So we have reviewed this. I gave you the formula. The half-life for a second-order reaction is, who can still remember the formula? Correct ni siya. Inversely proportional to the initial concentration. So I will place here CaO. Let's say, for example, if we're talking about A as the species, what's the other thing that should be present in the formula? Can you still recall? Half-life of a second-order reaction. It's the rate constant. Okay, 1 over K CaO is the half-life for a second-order reaction. Okay, here are markings here. Next. A certain reaction is second-order in A. When Ca is 0.03 mole per liter, the rate is 3 times 10 raised to negative 3 mole per liter per second. The rate when Ca is 0.015 mole per liter, the rate when C sub A is 0.015 mole per liters in mole per liter is. So you're going to look for the rate. The answer is already this one. Okay, I'll give you around 2 minutes. Please check how did this particular answer came about. That way I can also check from my end whether you know how to answer that one. A certain reaction is second order in A. So it's second order. You're given that when Ca is 0.03, the rate is 0.003, or that's 3 times 10 raised to negative 3. Now it's asking you what would be the rate if the concentration is 0.015 for this same reaction. I'll be back after a minute. Okay. 10 seconds, 20 seconds is gone. But can anybody explain to me what's the procedure to do here? You're given a second order reaction and you're given here rates and concentration. So what would be the first thing that you will do? You determine the what? Class, you determine the what? Okay, somebody wrote. You determine the
K-ness.
You determine the K. Thank you. You determine the K. That's more straightforward. So you are given the rate. Very good. K Ca squared. you have the rate equal to 0.003. You have K, and the CA for that is 0.03 squared. So you get the K. What's the value of the K? Hurry. What's the value of the K? That's 3.33. What do you do then? Next, what would you do then? You will go back to the same rate expression. Anyway, you are asked for the rate. So the rate now is equal to 3.33. That's the K. And then you see sub A, which is 0.015 squared. So you have the rate. That's very easy. So the answer is correct. You multiply to the new CA, which you need to raise to 2 or square. So what's the answer? That's 1. 7.5 times 10 raised to negative 4. Otherwise, there must be something wrong with the value given to me. Okay, that's very easy. Very simple. Now we go to the next. A certain reaction is first order in A. The specific rate is 3 times 10 raised to negative 3 per second. The half-life is, so you need to know the formula. The half-life is, for a first order reaction, is 0.693 over the rate constant. And that's it. You'll be getting this one. You will have 0.693 divided by 0.003. It will be giving you 231 seconds. Okay? So formula only. The key is the formula. Go to the next. Next. Okay, next. A certain reaction is first order in A. In 30 minutes, A decreases from 0.55 to 0.15. The time it will take for A to decrease from 0.35 to 0.15 is, what would you do? You're given here how the concentration changes over time. In 30 minutes for this first order reaction, concentration decreases from 0.55 to 0.15. What do you think is the purpose of this set of information? You will what? You will ln of Ca over Cao is equal to Kt. You will determine the same thing with the previous one. You will determine the K, correct, the K, it's the K, determine the K. So negative ln of 0.15 over 0.55 is equal to K times 30 minutes. So you know the K. So your K value is, what's your K value? K value 0.0433. It's first order, so the unit is per minute. Now then, using this new set of information, you find the time. So negative ln of this time, your final concentration is 0.15, the initial is 0.35. You use this K that you already determined previously and time. So the time will be this one, the 19.6 minutes. Okay, that's correct, Christian and Socrates for the K. Okay? It's a very easy problem in kinetics. Seems like it's not a board problem at all, but we have to start with the simple before we go to the complicated. Okay, that's it. We move forward. Here. A certain reaction has an activation energy of 125 kilojoule per mole. The rate constant is 0.033 per second at 55 degrees. The value of the specific rate constant at 100 is, what will you do? This is a direct substitution to Arrhenius, the extension of Arrhenius formula. So you have K1 over K2 equal to E over R. You have 1 over T sub 2 minus 1 over T sub 1. You have ln of, so your first rate constant is 0.033. The other one, this is unknown. K sub 2. Your activation energy is 125 times 10 raised to 3 because it's in kilojoule. You use here 8.314. That's in joule. Then you have here T sub 2. So T sub 2 would be this 100. You will have 1 over 373 minus 1 over this 1. Temperature is 55 plus 273. The answer is 328. So 328. You'll be getting the K sub 2. So please check if the K sub 2 that you'll be getting is 8.3 per second. It's per second because the unit of the first rate constant is also per second. So meaning your reaction is first order. Did you get the answer? So the answer is 8.3 per second. Okay, so then we move on because you already got the answer. Next. A certain reaction has a specific constant of 4.27 times 10 raised to negative 3 per second at 25 degrees Celsius and 7.35 times 10 raised to negative 2 per second at 80. This time, it's the activation energy that you need. The same formula. So you will have ln of, you have 4.27 times 10 raised to negative 3. The other one is 7.35 times 10 raised to negative 2. This would be equated to the activation energy over 8.314. And our temperature here will be the temperature at 80. So you're in Kelvin. So 1 over 353, and the other one is in 25 plus 273, that would be 298. You'll be getting the activation energy here. Your answer there might be around 45,000 because this is already in kilojoule per mole. Okay, so please check if you'll be getting the same answer as the one that is checked. Did you get it? Activation energy. Are you solving there? The actual answer is 45,250.47. So in kilojoules, it's 45.2. Okay, kilojoule per mole. Okay? Sige. So I am glad that some are with us, solving as well. You may find this very elementary, but you cannot start with the complicated unless you start with this. Now, a third order gas phase reaction. Is this the next question? Okay. A third order gas phase reaction, 2NO plus O2, forming 2NO2, has a specific reaction rate of K sub C. I will increase this one. Equal to 2.65 times 10 raised to the 4th liter squared per mole squared or gram mole squared per second at 30 degrees Celsius and 1 atm. The value of K sub P, take note, in gram mole per liter per atmosphere cube per second is. Now, how will you determine the answer here? So the answer is 1.7239. How do you get that answer? What will you do? You will simply what? So it's a gas phase reaction. So meaning class, you will have, instead of concentration, partial pressure. But the thing is, the specific reaction that is provided is in terms of concentration. You see this subscript C? So it's in terms of concentration. There's a need for you to have it converted in terms of partial pressure. Because if it's a gaseous reaction, you're not using concentrations, but rather partial pressures. So how will you convert your K sub C to K sub P with this set of units? How will you do that, or how will you accomplish it? That way, even though, so this is a gaseous reaction, even though it's gaseous and you're going to monitor the rate of the reaction based on the changes in the partial pressure of the components here, nitrogen oxide and oxygen, your final set of units for the rate is still in terms of mole per liter per second. But you will be provided with partial pressure of your components here, NO and O2. How will you do that? How will you convert K sub C to K sub P? You will do, it's like you have this. And you are provided with K sub C. And what you're going to multiply to it is P sub A. Or that should be P sub A and P sub B. If this is elementary, and let's say this is species A, and this is species B, you will have P sub A squared P sub D. Something like that. If these two, the P sub A and the P sub B at any time will be equal, we can write it into a simple third order reaction wherein we only have partial pressure of A, since we have concentration of A in here. So you will have K sub C, P sub A cube. Because anyhow, we'll be dealing with just the units. You're trying to find a way of converting the K sub C to K sub P. That way, you will still have the units of mole per liter per second in spite of having to use partial pressures in lieu of concentration, which is in mole per liter. How would you do that? How will you convert? So this K sub C is to be converted. Now I erase it. It has to be converted to K sub P. Because K sub C is only used for C sub A and C sub B. How will you do that? It's actually quite simple. You just have to deal with the, you see here, the set of units that is given. The K sub B should have a unit of gram mole per liter. Or let's say mole per liter per atmosphere cube per second. Now, if you recall our discussion on conversion of K sub C and K sub B, then we have a conversion that happens in both sides of the equation. We convert the concentration here in terms of partial pressure, and we convert the K sub C here in terms of K sub P. In this case class, it's different. The set of units for the rate of reaction is kept at mole per liter per second, while we have to work on partial pressures. So this is how you're going to do it. The K sub C value that you have, in order for it to have an atmosphere raised to 3 unit, is of course to be divided by, so I'll place here K sub B is equal to K sub C divided by RT I will have it raised to 3. Now, how did I know that it would be something like this? Because I noticed that there is already atmosphere cube in the denominator. So since this atmosphere cube has something to do with the order of the reaction, which is third order, as stated here, if I will work on the value that is given, which is 2.65 times 10 raised to 4, I'll write here liter squared per mole squared per second. The denominator, the R that you're going to use, since you have the liter and the mole and the atmosphere here, that should be the 0.08205. The unit of this is ATM, liter per mole, Kelvin. This one should be multiplied to the temperature converted to Kelvin. So this should be 303 Kelvin. This entire expression has to be raised to 3. How did I know that it would be raised to 3? Because of this. It's cube. So you will have now the cancellation of the mole here. And since this is cube, so the liter squared and the mole squared here will cancel with the liter and the mole here. But there's a remaining liter per mole unit here in the denominator together with the atmosphere, which is raised to 3. The remaining unit in the denominator only is liter per mole because you already canceled out the liter squared and the mole squared in the numerator. So your K sub P then is equal to, you can do that. It would be something like this, I think. The value would be 1.7, let's see. You will have 2.65 times 10 raised to 4 divided by the quantity 0.08205 times 303 raised to 3. So it's 1.7246. So your set of units now, the mole goes up, so mole, the liter remains here, and you have the atmosphere raised to 3, and you have the unit also for time, which is in seconds. This is really, class, very self-explanatory, because if you're going to write your rate in this form, wherein your set of units will be mole per liter per second, your KP should have this set of units. I will just write the set of units. So you will have mole per liter per atmosphere cube per second. Remember that you're not going to use concentration, but you're going to use partial pressure. And the unit for partial pressure, is this one, is atmosphere raised to 3 because it's a third order reaction. So these two cancels, leaving you with the unit, the usual unit of expressing rates of reaction, which is mole per liter per second. That's the answer, how you got the answer here. So this is on the premise, class, that even if you're given a gaseous reaction, the final set of units for the rate is not in terms of partial pressure, but rather concentration per unit time. Okay? So in here, if I will summarize, I'll use a different color because it's really hurting my hand. So you will have your K sub P equal to K sub C divided by RT raised to N. This is in the case wherein the rate of reaction, as I have said already for the third time probably, is in terms of concentration per unit time. So this is how it's going to be. This is how you should convert your K sub C to K sub P or vice versa. So take note of this formula because this was not covered in the slides that I gave you. Okay? Now, actually, you are to base your answer for the KP, the numerical value of the KP, based on the set of units here that the problem also specified. Okay? If the set of units is not this, there's another way of getting the K sub P actually. I will erase this one so I can show it to you. I'll erase the red ones here. Do you have any question in here, by the way? None? Sige. So So I will raise hand so I can show to you what I mean. That in this particular question, the K sub P is solved using that particular formula because of the step of the specified set of units that it should have. Without that particular set of units, then there is another way of determining the K sub P. And I know you can recall this in our discussion then. Let's say you're given dCA dt equal to K sub C, C sub A. Let's say this is raised to n. And we would like to express this rate in terms of pressure, partial pressure. So meaning I'm expecting that this one will be converted to dPA dt. How am I going to do that? So from your ideal gas law, if you divide by V RT, you will have N over V. On the right side, you will have C sub A. On the left side, you will have P over RT. That would be partial pressure of A divided by the product of the universal gas constant and the temperature. So we will replace the C sub A that you have here in terms of partial pressure. So you will have negative of the P sub A over RT divided by dt. Okay, you change the entire CA. And you will have here K sub C, it's still C sub C, K sub C because we have concentration here. I will change the concentration in terms of partial pressure as well. Okay, we raise this to n. Now this is a constant, it will not participate in the differentiation, it will be just simply placed before the derivative. So I'll just get this one here and I'll take one here. So but it still has remaining exponent, whatever the n is. The left side now is converted to dPA dt. So this is what I mean that you have a gaseous reaction and the rate is not in terms of concentration but the rate of change of the partial pressure. In this side, you will have K sub C over, so this RT, I already took one, so this would be RT. This time, this is N minus 1. This is N minus 1 because I already took 1. This is raised to N and this is raised to N. And you have it multiplied to P sub A raised to N. This entire expression that you have here is K sub C over RT raised to N minus 1 is your K sub P. Based on this scenario, that your rate is in terms of partial pressure. So meaning you expect that the problem will stipulate that your rate will be having the unit atmosphere, for example, per let's say second, because it's in terms of partial pressure and time. Then this is how you're going to solve for your KP, given the K sub C. You get it? In this problem, we solve it differently because of the given set of units for your KP. It is already giving you the end set of units for K sub P, which tells you, class, that from the mere fact that you have your gram mole per liter, you still have the left side in terms of the change of concentration per unit time. Because of this, because you won't have this if not for the fact that the left side is still in terms of concentration per unit time. Because you won't have any concentration here. You will already have here partial pressure, as I've said, because you're dealing with the gaseous reaction. Okay, but for this particular problem, this is the answer. The one that was taught to you when you were taking up chemical reaction engineering is this, wherein since it's a gaseous reaction, the rate was expressed in terms of partial pressure per unit time. So this is the formula that was shared to you. This is a different problem. This was taken from a reviewer wherein you have already a specified set of units for KP. I'm explaining this because I don't want you to get confused. There are times wherein the problem gives you the desired units and it's different than the ones that you have learned in the past already. Primarily because of the difference in the required set of units also for the final answer. So this is the way it should be. This is really the answer for this problem. Do you have any questions? Okay, di na lang tayo mag-break para diretso I was having in mind that I'll give you a 10-minute break. So we will just move on. We go to the next slide, and that's slide 36. So we have this one now. Equal moles of y and z are mixed with x. This is one very confusing problem actually, class. You are given equal moles of y and z, which are mixed with x and allowed to react for 1 hour, after which time half of x had reacted by the reaction. If the reaction with respect to x is first order, how much of x is left unreacted after 2 hours? Actually, it's very easy, but it was made confusing because of the first statement. Equal moles of y and c are mixed with x. So you will have in mind that x is reacted with y and c, and they are allowed to react for 1 hour, after which time half of x had reacted. So we could get here that at t equal to 1 hour, you have x sub a equal to half. So you have 0.50. Half of x had reacted. If the reaction is first order with respect to x, how much of x is left unreacted after 2 hours? So how will you write your rate law in this case? Will this have bearing? This one equal moles of y and z. If this one is specified here, the reaction with respect to x is first order, your rate law would be very simple if I'm going to write here. So your rate law will simply be K C sub A, or in this case C sub X, because we're talking about X. Yes. C sub X. This would also be X. Okay. If it's first order with respect to x and we're given conversion, the formula that you will use is a simple negative ln of 1 minus xa equal to kt. This thing about the dimension of the y and the z does not have anything to do with the manner you write the rate law. Okay, so this is taken also from a reviewer. So if you have this, it says there that 50 minutes after 1 hour, you have 50% conversion. So this is just one, right? 1 hour. So you will have a corresponding K value here. Once you have the corresponding K value here, you use that in the next condition. How much of X is left unreacted after 2 hours? So you will have here 1 minus XA. You use the value of the K that you have here and you place your time, which is 2 hours. The XA that you will be getting here will give you the answer for this. It will not give you 0.25 CAO, but you will have to answer it like this based on your answer in here. Actually, the choices I place here actually is wrong because they should be XA or XO, because we're talking about X, Y, and Z. So I'm so used to CAO. So please check if you can get the same answer as the one that is checked here on the choices. Did you get the same answer? We can proceed to the next item if you have the same answer. Did you get it? Are you still there? Okay. So the XA that you'll be getting is 0.75. But the question is not the XA. The question is how much of X is left unreacted. The one that is left unreacted is of course the 25% because the 75% was already reacted. Yes, correct. Your unreacted would be 1 minus 0.75. So that is why your answer there is 0.25. So this is the one that I was mentioning to my students right now, that some problems in kinetics would ask you a question that is related to the thing that you are solving. But the thing that you are not solving is not yet the answer. It will just simply point you to the answer. So this is a very simple example of such scenario. You determine the conversion so that you can answer this question of how much is left unreacted. If you're not very careful with having to read this particular question, you may answer that it's 0.75. Although among the choices, it's not given. But if it's given there, you will answer 0.75. Of course, you'll get wrong because what is asked is the portion that was not reacted, not the portion that has reacted. Okay? Okay, I will clear my markings here. For the reaction, which is here, you could see a series reaction where your rate constants in the first and in the second steps are equal. The initial concentration for both B and C is 0.5 and CaO is equal to 2.5. The time at which concentration of B is maximum is. Now, if you recall in our discussion, I gave you a formula that was solved for the time in which the concentration of the intermediate B is a maximum. But that particular pre-derived formula is only good when your K sub 1 and K sub 2 are not equal. This is if I'm not mistaken, this was given to you as part of your problem set then, wherein you are to derive a separate formula that you can use whenever you're given a two-step series reaction where the rate constants are equal. Can you still remember the formula that you were able to derive for this series reaction in which K sub 1 and K sub 2 are equal? You can't remember the formula. You're given the CaO as 2.5. You're given B and C initial concentration as 0.5 and K1 and K2 equal to 0.35. If I'm not mistaken, I gave you the exact thing in here just for review purposes. And you are asked to determine the time when B is maximum. Now, how would you go about it? I will just share a new screen so that I can do this thing in the Jamboard because the space here is limited. Just okay. This you did already last time, so we'll do it here again. So you have A forming B, forming C, and you have here K sub 1, K sub 2. Okay, that's your reaction. When you write your rates here for a series reaction, you do it step by step. So we process it based on the first reaction, then we go to the second. So based on the first reaction, it's just like any other reaction that you have learned. You consider the steps here as elementary. So this is a first order reaction. So you will have something like this, and you have K sub 1 dt. Now, if you will integrate from CaO to Ca, from 0 time to T time, you will have ln negative of Ca over CaO equal to K sub 1 T. If you'll transfer the negative sign in here and raise everything to E, you will have Ca equal to CaO E raised to negative K sub 1 T. I'm sure some of you could still remember this. This first equation allows you to solve for the remaining amount or the concentration of A after some time the reaction has already proceeded. So this is your formula. Given the time, you can solve for the concentration of A. Now, as for the B, you will have to write the net rate of reaction in terms of component B. So if you will consider it as, let's just have this, sorry, I'll use this one. I'll consider the B here as positive. You will have, or product, to make it positive, then you will have K sub 1, C sub A. And in here, it's a reactant, so you will have minus K sub 2, C sub B. Okay? Now, this one, you can place here dCB dt. And since K sub 1 is equal to K sub 2, which is 0.35, so I can place everything as K sub 1, or I can simply represent it as K. Anyway, they're just equal. So I'll place here K plus K C sub B, this one transferred here, and your K sub 1 CaO E raised to minus K sub 1 T. Now, why did I change the C sub A here in terms of CaO? Because I want this to look linear, and if I will keep the C sub A here, I cannot process this as a linear DE because I will have now two concentrations. I need only one concentration with time. That way I can evaluate my DE. So this should be your DA now. Your Ca was replaced by this one, CaO E raised to K sub 1T, or that would also be simply K because they are all the same. So para hindi na tayo mag-change, magbutang subscript, it's all K. Okay, so this is K here, and you'll have here K because they're the same. So for a linear DE, you need to determine the integrating factor. So it's E raised to K dt, and this is E raised to KT. The answer for this particular linear DE will constitute your unknown function C sub B multiplied to E raised to KT, your integrating factor, and it's equated to the integral of this one. I'll write this K sub 1 also as K CaO E raised to negative KT, have that, and then multiplied to this particular integrating factor, so E raised to KT. You could see right away here that this would be a simple case of E raised to 0, or that would be 1. So your left side would be C sub B E raised to KT, and your right side would be K sub 1 CaOT plus the arbitrary constant of integration C. You get to determine this C after you substitute the initial condition that is given in the problem. So I'll show that to you on the next slide. So at time equal to 0, if you use the initial condition, your initial concentration for B is, let me check on our slide. Your B and C is 0.5. So it's 0.5 mole per liter. So we go back to this equation that we have here to find the C, the arbitrary constant of integration. So C sub B will be 0.5. You have 0.5 E raised to 0. And you'll have here, this is also 0 because your time will be 0. And you will have C remaining on the right side. So the C is equal to 0.5. So you will have C sub B E raised to KT here, and you will have K CaOT plus 0.5. Now, wait, you have K, correct, K1 CaOT. You have that here. Now, your C sub B could be written generally here as equal to K C sub AOT E raised to negative KT plus 0.5 E raised to negative KT. What I did, what you should do is you divide this equation by e raised to kt. So that is why you have it written here as negative. Now, if you go back to the problem, it says, go back to the problem. So it says there that time at which concentration of B is maximum. Time in which the concentration of B is maximum. So we go back to our solution. In order for us to get the time and concentration of B is maximum, we use maxima minima. You differentiate this formula of yours that solves for the concentration of B at any time. So you differentiate it, of course, with respect to time. So when you differentiate it with respect to time, you will have here your K and CaO, they are constants. And you will have here to use product rule of differentiation. So first term times the derivative of the second, this is multiplied to negative K, plus the second term times the derivative of the first, which is just the 1. I already set aside the KCAO. For this second term that you have, it's just the derivative of the exponential function e raised to u du. So this would be multiplied by negative k. You know already what k is. Then we set this to 0. Of course, this does not matter much anymore because we can divide the entire expression by that and your left side would still be 0. In here, you will be left with negative kt e raised to negative kt plus e raised to negative kt. This one is minus still, minus 0.5 k e raised to negative kt. All of these expressions have e raised to negative kt. So e raised to negative kt, e raised to negative kt, e raised to negative kt. So we can have it cancelled. So we take this out. Okay. Please transfer to the next slide. So we have negative kt. This is gone. This is left with 1. So that's 1. And this is negative 0.5 k. So I have here transferring this on the other side, or this one I'll transfer here, you'll have kt equal to 1 minus 0.5 k. Okay. Yes. Base ang CaO. Oh, let me check. Sorry. CaO. Okay, I have here KCAO. Okay, and the other one I don't have. So I need to multiply the first two terms by KCAO. Wait. Okay, I cannot either cancel the K because this one has K. Okay, so the CA only is kept. I'll use a different color. Your CAO is kept here, class, but we can cancel the K. So I'll take out the K here. Right? So this will be now 0.5. I'll take this out. Okay, you have that. And the first two terms here, correct, we still have CAO. So we'll just insert the CAO. I'll just move it here. So I will have this CAO multiplied to these two. Right? That's it. Now with these two now, I took out, so I will have the CAO here and the CAO here. So next slide will have CaO in both of these terms. And this is not here anymore. So CaOKT, we need to have the CaO there and CaO only. Negative, and this one is CaO. Plus CaO. And we have 0.5 because this one is taken out. Same thing with the K here. So we go back, we transfer the negative term here on the left, so you have CaO, and you have here, I'll just erase everything, guys. So this was transferred here, and the right side would be CaO minus 0.5. If I want the time, the formula for the time, that would be CaO minus 0.5 divided by CaOK. The time when B is maximum. This is our formula in determining B. I'd like to underline this because this would be the formula that you can use in determining the concentration of B at any time. To get the time in which B is maximum, that's the requirement in the problem, you differentiate this with respect to time. So we did that. I set this aside and use your product rule of differentiation here. This one is differentiation in here, differentiated in here. If you equate this to 0, the K in this K will just cancel each other, and you'll have 0. What is left here is CaO. And I copied everything here, the same thing in here, and that one there. So this, just like I have canceled the case in here, after equating this to 0, you can also take out the exponential functions. So this is your formula here now. You want the time, place it on the left side. You have this. So this is your generic formula to use whenever you're given a two-step series reaction in which the K's are equal. This is it. So in our case, you just substitute the given data. So in case of the initial concentration and the K, so that's what we need. The initial concentration is 2.5 for A and 0.35 for K. So we will substitute that to our formula. So CaO is 2.5 minus 0.5 over 2.5 times 0.35. So check the answer. You have 2 in the numerator divided by 2.5 and divided by 0.35. So you have 2.29. Okay, let's check. 2.286, or that's 2.29. So let's go back to our slide. So you have it already rounded off to 2.3. So the formula that we just derived, you can write it in your summary of formulas. That's for the case wherein your rate constants are equal for your two-step series reaction. Whenever you encounter such problem, you need not derive it because you already have it derived. And you just substitute the given information in the problem. Okay, let's move on. Any questions so far to what we did? You did that actually also last year, second sem last year. Okay, so you have this one now, same scenario, it's a continuation. So the concentration of C after 2 hours. So it's asking for the concentration of C after 2 hours. How would you determine this value of 1.1416? The concentration of C after 2 hours. Anybody who knows what to be done here? You already have, I'll go to our solution, go back to our solution. You already have derived the formula for C sub B and C sub A. But that particular problem is asking for the concentration of C after 2 hours. So C sub C at T equal to 2 hours. What will you use? What fundamental principle in series reactions will you use? That way you can find the C sub C. Can you recall, based on our discussion for series reaction? Okay, did you recall this? The total number of the sum of the initial concentrations, or the sum of the concentrations at any time, should be equal. So the sum of the concentrations of the species at any time for a series reaction should be equal as long as your stoichiometry is this. Okay, the sum would just be equal. So using that, what do we do then? To get C sub C, this is our goal. To find C sub C. How do we find C sub C? So based on the formula that I have written here, C sub C is equal to CaO plus CbO plus CCO minus C sub A minus C sub B. What do we do? C sub C is equal to CaO is 2.5. Our C sub B and C sub C are equal. Let me check. It's 0.5 pound mole per cubic feet. 0.5. So we'll have here 0.5 plus 0.5. What about these two? Where will I get these two? I'm already pointing out to you the procedure. You'll get the two from the formulas that we have derived already. You use this one and this one. You just substitute the values here and T equal to 2. So for CaO, e raised to KT, this is CaO, so 2.5 e raised to negative 0.35 times 2. This is for the Ca. Our Cb is quite long, so your C sub B would be KCaOT minus K. I'll write it here below. 0.35 times 2.5 KCaOT times 2 KCaOT 0.35 2.52 e raised to negative KT. E raised to negative 0.35 times 2. Okay, what about the second term for the C sub B? Plus. Since we have minus there, so it should be minus. Minus 0.5 by the way, class, this is minus. So this is minus 0.5. Very forgetful. 0.5 e raised to negative k. E raised to negative 0.35 times 2. You just add this. This will be 3.5 already. Subtract this and this and this. That should give you the C sub C. Can you please solve for C sub C? the answer for C sub C should be 1.1416 or something close to that. 1.1416 or 1.1416. Did you get the answer? .6207. Okay. So Vincent got 1.141. Okay. So that's it. So if we go back to our slide, answer is 1.141. Okay. More or less in that range of values. Okay. So we haven't actually covered any of the parallel, homogeneous catalyzed reactions, autocatalytic reactions, and reversible reactions. If we're going to talk about kinetics applied to integral analysis of constant volume systems. Okay, so far this is what we have covered. So we will continue this next week. We have this. How many do I have here still? 1, 2, 3, 4, 5. Okay, that's only 4 because I think this one is variable volume. So after the 4 problems here, we'll go to variable volume, and then that's the time that we'll go to reactor design already, because we'll not cover differential analysis anymore, because the process of finding the rate law for differential analysis is graphical. It's purely graphical, cannot be done using your calculators, per linear calculators. So do you have any concerns regarding the problems we have solved tonight? There's none. So there's none. I'll stop sharing now.